As I talked that we have now with us today, we will talk about some defects in solids. You might have heard about it earlier. I don't know whether you have studied it or not. आपने ये पहले पढ़ा कि नहीं मुझे नहीं पता, पर ये बहुत एक जरूरी चैप्टर है और सेक्शन सी में है आपके जो ए बी सी सेक्शन है. So this is in section C we are talking about, and I will cover up some of the aspects and also have some assignments for you to complete in this regard. And I will just discuss some technical things because there are certain things which you can read and they are just theoretical. So I'm just doing the conceptual building at this point. So let me share with you this screen and um, okay, so this is okay. So in fact, I have taken my slides, which I already have recorded this module in EPG Pathshala. So in MHRD UGC, you will find a page EPG Pathshala module. There, this is also a recorded lecture over there. So I've just taken this module, and the learning objectives are classifying different type of defects such as point defects and line defects, and classification of point defects and thermodynamics, and other defects are not there in your syllabus. So I will just cover up these two defects, point defects and line defects today, and leave rest of it is okay. Yeah, so these are not required. So crystal defects. So it says a perfect crystal is an idealization. There is no such thing in nature. Atomic arrangements in real materials do not follow perfect crystalline pattern. What does it mean to say is this, that when you are drawing your lattice, when you are assuming it to be perfect, that at each lattice point you have an atom or a group of atom which is called basis. This is a very ideal situation. In a real physical sense, we do not have ideal crystals. We will have, you can say that some of the defects are inherent due to the while production, when some material is being synthesized or produced in the laboratories or at industrial scale. So there are defects associated, some impurities are there. But even if you try to ensure that 100% purity, is still the thermodynamics equilibrium does not allow the system to be perfect. It always says in our thermodynamic system that at any finite temperature there is an entropy. So there is a disorder into the system, and this entropy is not zero. It cannot be zero. Okay, so there is a thermodynamical reason also for these defects to exist in systems. So here we have three kinds. This is zero-dimensional defects. These are vacancies and interstitials. One-dimensional defects, dislocations. So we will cover only this 0 and 1. Okay, this 2 and 3-dimensional defects are not concerning with you. So I will not talk about them. Okay, so let's understand. You see this picture in this pictorial way, that first we will talk about the point defects. So if you have a crystalline system, crystalline lattice is there. So what you see here, you can see that at some point, this lattice where my cursor is moving, one atom is missing over here. So in ideal perfect crystal, one atom should have been here, but it is missing from here. And as a result, in this location, this lattice is distorted. So this also causes a local distortion in the bonds and interactions, and so like this. So this is one kind of point defects, which usually exist when some of the atom is missing from here. And now this picture, that was some illustrative example, or was a drawing by some hand or with the help of software. But what you see here is a real picture of a silicon surface. I think it's a silicon surface using STM. There is something called scanning tunneling microscope. So if you have the crystal and you just scan the surface of the crystal, and you can see the where are the atoms are sitting over there. So this which you find atoms, these are nothing but density of states of electrons, because where you will have uh, more electrons, tunneling current will produce. So in a way, indirectly, it is telling you the atomic positions. So you can understand, you can forget about details for time being and think that these are atomic positions. So you can see where this arrow is. You can see that one of the atom is missing here. So you can see the direct observation of the defects on the surface. One atom should have been here. This is just 5 atoms. Generally, it makes a hexagon ring, and you have 6 atoms. But you can see that one of the atoms is missing here. So this is a direct visualization using scanning tunneling microscope. And this point defects, we can really see that. Now, another type of point defect is that if, let us say, instead of vacancy, if you have some extra atom placed in the interstitial position. So interstitial position is somewhere like this. You in between atoms, you have some empty space, and somehow if you squeeze one atom during the course of production of material, or thermal annealing, or something, some implantation, sorry, not thermal annealing, but implantation, such of the impurities can arise where one of the atom can be found inside the interstitial positions. This is self-interstitial. Why it is called self-interstitial? Because the same kind of atom over here, but it can be some impurity atom also, which is not this kind of atom, but some other atom. Maybe, for example, this is sodium, and this is, let us say, potassium, or this is potassium and this is sodium. So then that is not self-interstitial, but this is the case of self-interstitial, because if you have a sodium here, you will also have a sodium there. So here also you will see where there is a defects, there is a local distortion of the bonds and atomic lattice. It's locally distorted, and this distortion from this center extends to certain region in the space, and after some distance you will see that again you can see the lattice is perfect. So these are the imperfections associated with the lattice, and these are called point defects. So now generally it is defined, this point defects are of two kinds according to their definition. That's a Frankel defect, and another is a Schottky defect. These both are point defects. So what happens in Frankel defect is that, for example, you have a crystal like this, and some of the atom from here is missing, and it goes. You remove it from here and put it somewhere in the neighboring interstitial. So you create a vacancy and also create an interstitial at the same time. You remove one atom from here and place somewhere in the interstitial around. So that's a Frankel defect. So it is like energy needed to remove an atom from its lattice site to place it in somewhere in the interstitial position. So this is a type of a Frankel defect you will have. In Schottky defect, you will see that uh, one of the atom present here is not anywhere in the interstitial, or one of the atom removed from here is not anywhere in the interstitial, but it has gone to the surface of the crystal somewhere outside. So it does not exist in between. So when you have this kind of defects, where this removed atom does not remain inside the interstitial of solid, this is called Schottky kind of defects. And uh, you always need a charge neutrality, because any system you take, let us say sodium chloride or potassium chloride or cesium bromide, whatever ionic crystal you take, this has to be charge neutral. So if you, let us say, you have one positive charge removed from there, you will have one negative charge removed from there. So this is somehow way to um, uh, ensure that there is a charge neutrality. In this case, there is no problem because the same atom which was there, it is already in the interstitial. So naturally, you will see that energy required to remove one atom from here and to place in interstitial will be different from the energy required for an atom to remove from here to put it on the surface. So naturally, you have this F of R. This is a activation energy required to remove an atom, and this is S means Schottky, and this Fr means Frankel here. This derivation we will do now, just in the next slide. What it tells us, this is the Fr, number of Frankel defects in thermal equilibrium at some temperature T. K is a Boltzmann constant. N is the total number of atoms in the systems or molecules, whatever the case may be. Similarly, it is here. Okay, so this is how Schottky and Frankel defects are defined, and naturally this energy required to do such an operation would be different in different cases. So this is Frankel and Schottky. Um, so this is the formula which tells us number of defects here. NV is a number of vacancy. Basically, you can take it a Frankel type vacancy or Schottky type vacancy, and these are the total number of defect site possible. It is basically the total number of atoms in the lattice, and activation energy, and depending whether it is a Frankel or it is a Schottky, and Boltzmann constant and temperature. This has been explained here. The value, generally it's an written, this is the value of a Boltzmann constant in joule per Kelvin atom, and the same is converted into electron volt per atom Kelvin. The same is converted into electron volt per atom Kelvin. So this is the description of this equation, and how this equation came, actually where from this equation comes, that is your assignment, and I have given a hint for this assignment, so you note this. Either you can take um, the snapshot of this, you can take the screenshot, or you can write it. I will wait for a, let's say, 5 minutes on the slides, so that you note. The assignment is clear. Derive the expression for equilibrium number of point defects n, Schottky and Frankel. It can be any of it at a given temperature T, if the total number of atoms in a given solid is n. So this is the task, and a hint is given to you. So in the hint, what you have to prove, this is also here where my cursor is. You have to prove this. And hint is given, the number of ways in which n defects can be produced out of n atoms is given by, this you already know, this is a formula of combination and permutation. So this is combination. If you have n lattice sites, and out of which you have to produce n defects, and the relation between this thermodynamic probability here and entropy, this you know. You also know free energy, E minus Ts, S is already expressed here, and E is the total energy in producing n defects. If you have Eg energy required to produce one defect, so there will be n Eg energy to require to produce n defects. So that's how it. So I have provided you a hint. A lot of things are given over here, and also it is written in equilibrium concentration of defects, the free energy is minimum. So this free energy will be minimum when there will be equilibrium concentration of the defects. So you would like to know with respect to what you want to minimize this free energy, or with respect to what differentiate you will differentiate this equation. And when you differentiate this equation, when f is minimum, so that differential has to be zero at minima or maxima. Any differential is zero. So this is the hint over here. So I have given you this, and you have to drive this. And what you can do is, when you derive this, you can do it on your page and pen and paper. And there is a software app called Cam Scanner. You can just uh, combine it into a one PDF file, maybe 1 page or 2 page, whatever it may be, and send it to me by email. So this is not very difficult. I guess every one of you can do this. This is I have provided you enough hint in this how you can derive this formula, and you can actually get this with certain approximation. Remember, this is some sort of approximation where n is much less than n. So total number of atoms is the Avogadro number, almost equal to, depends on how much is the material. So the n will be very less as compared to n. So this formula is not an exact, but some sort of approximation, and that approximation will be true when n is much less than n, capital N. And if it is large, then this formula is not true. Then some formula has to be there. You can also find out that. Okay, so I hope if you have copied it, I will just, I think, move forward. If you have copied this, this is your assignment task. So enough it is given for you to derive this formula. Now I move forward and give more about on this. So it is written in a different way. Here ND is actually the number of defects. This is small n we are talking, and this is a capital N. And as you know that this term is an exponential. So with respect to t, if you plot, it will be exponentially increase. So you see, you are not changing QD. This is some minus term and it's constant. So if you increase t, so um, ND upon N, and with the number of temperatures, so you have this increase exponential with the increase in temperature. When temperature is increasing, yes, when temperature is increasing, this negative number is decreasing, and this negative number decreasing means this exponential will rise, because it will become large and large and large, so that the number will become smaller and smaller, and this is a negative number. So when it becomes negative smaller, so this will rise like this. So if you plot, take the log on both sides, so you have log nd upon n, and this exponential goes here. And instead of plotting now t, you plot it with 1 upon t, you will have a straight line like this. So this is called Arrhenius plot. So generally, you can find activation energy from here if you can have such a plot. So at a now the temperature is increasing in this side. As the temperature is increasing, the number of defects are increasing. So at any finite temperature T, there will also be some concentration of defects, as we were saying. However pure the material may be, there will always be defects at some finite temperature. Only at absolute zero, which you cannot achieve, you can expect a perfect crystal. That's some sort of idealization. So this is thermodynamically we are talking about. But there are different ways of producing a defect. System is also, it's very difficult to produce a pure system, 100% pure system. There is always an impurity. So that is again an added defects into the system. So the benefit of it is like this, that if you know the slope is nothing but minus QD upon K, and K, it's a Boltzmann constant. So with the help of the slope, you can find out the activation energy. So if you have to get the activation energy of any system or defects, that's how you can calculate. So you have to know that how the defect concentration is increasing with respect to the temperature. This can often be experimentally measured, where defect concentration can often be experimentally measured with the help of this technique called positron annihilation technique. So that allows us to measure the defect concentration with respect to temperature, and you can find out then the activation energy. So its order is also told you. It's typically 1 electron volt. So typically 1 electron volt means it can be 0.2 electron volt, it can be 3 electron volt, anything somewhere like this. So it's of this order around. And at room temperature, this is also told that the concentration, the defect concentration is 10 raised to the power minus 70. So you see, this is also very low. So our approximation we were talking about in the last slide is going to be very correct, because you can see this ND is very, very much less than N. 10 raised to the power minus 17 is coming. So it is telling us that if you have 10 raised to the power 17 atoms, there will be one defect in that 10 raised to the power 17 atoms. So this is a very, very small number of defect is there at the room temperature. Now, this is also a numerical example, and the we have given here some initial parameters, and you need to calculate this equilibrium number of vacancies in 1 meter cube of copper at 1000 Kelvin. So if temperature is 1000 Kelvin, how much would be the number of vacancies in 1 meter cube of copper? And this also, I leave this example for you. Answer is also given below. You can see that in 1 meter, 2.2 10 raised to the power 25 vacancies would be there. So answer is given to you. Density of copper is given. Atomic weight of copper is given. Activation energy 0.9 electron volt it is given, and Avogadro number. So you can take the snapshot of it, and this you have to derive yourself, to get this number actually. So ND upon N is coming out to be 2.7 10 raised to the power minus 4. And here you see that there are in 1 meter cube of copper, these many number of atoms are there. So if you multiply with this, you get the total number of vacancies. So this I want you to do yourself. This is a numerical example, and this kind of numerical example you can face. Okay. Okay. So now you can see that okay, sorry for this interruption. You can just note it, and I just go forward. Okay, so I just want to give you an example here, how important the defects are in condensed matter physics, and what is an important role they play in science or everyday thing, technology which we use today. You are very much well versed with the semiconductors, and you have N-type semiconductors and P-type semiconductors, which are shown here. So this is intrinsic semiconductor, where you have all silicon atom which have a tetrahedral structure in like this. And if you remove, let us say, one of the atom from a site and put a boron here, boron is I guess trivalent, and if instead of boron you have phosphorus, you have this is pentavalent. So this is by introducing some controlled amount of impurities into the semiconductors, which you call doping, you can produce semiconductors of the desired properties, which we have desired band gap, conduction, and all. And you can see the entire semiconductor industry now. You can see the microprocessors in your mobile phone, in computer, everywhere. So just introduction of limited amount of controlled impurities does so much good. So here the point is that it is not only that purity of the substance is good. In some applications, you require them to be very pure. But in certain applications, you need to dope them with some controlled impurities. So you want the system to be impure to perform according to the way you want it. You want to change its band gap. You want to change its conduction properties. So in the same way, if you produce a defects in the system, it also just, just hello. Sorry, uh, I think I now you have sound. I think is it okay? Now you can hear me. There was some problem with the sound.
Yes, sir.
Okay, okay, good. So, uh, so you see, this I was talking to you that these are the importance of defects in this into the system. That if you are having a desired concentration of defects in the pure systems, that is how you can uh, produce a very good material for desired application. Now, I will talk to you something called color centers. This is in relation with this point defects, actually, uh, related with this point defects. What are the color centers? So you see that, for example, let us say you have here this NaCl system. Generally, this kind of systems are alkali halides. Alkali halides means you have here one side alkali atoms like sodium, potassium, lithium, and cesium. Another side you have halide, chloride, bromide, and what else? Fluoride, like this. So this is a halide system generally in this kind of crystals. So for charge neutrality, you see that instead of one sodium here, you have one strontium. So this has two plus plus valency, and one of the vacant site is missing here. It still has charge neutrality because one charge, one atom from this site is missing, which is positive, and instead you have two positive charges here, this side. So that also produces a charge neutrality. On the other hand, you may have some chlorine atom, let us say missing from an atom, and it could be somewhere placed on the surface, or some sodium atom can be missing from other place to make it a neutral. So charge neutrality is very much required here. So here you can see this, this is the smaller atom is a sodium and larger is a chlorine one. This blue is a chlorine one. So what's the color system? If you just see this, let's say if chlorine atom is missing here, so here you have an increased positive charge concentration because you have this positive charge is here and one of the negative uh, ion is missing from there. So if this one electron is trapped into the system, then it makes a bound electron system here. You see, if you have a material and it is in touch with something, it is put on table or earth or something. So earth already is a reservoir of electrons, and so electron can come from anywhere. So this or it can come from the cosmic cosmos, and some rays, ultraviolet rays, or some cosmic rays, which produces ionization in the air. And one electron, getting one electron from anywhere is not very difficult. So if instead of this chlorine ion, some of the electron here is trapped in this side, because now it will be trapped because it will have a positive attraction from all this side, and this electron will be bound in this position. So this will form an atom-like system. It's a bound system. This electron is trapped here. And so you can think of this electron as a particle in a box. So this particle is bound in a box. It cannot go because it is bound by a attractive force from this positive ions over there. So when it is bound, it will form a um, some atom-like structure or particle in a box. So you can see that here, this is the energy which is representing a particle in a box, and it will have energy levels. This n is equal to 1, 2, 3, 4. So it will have 1, 2, 3, 4. And L is the dimension of this box. So this L is nothing but this dimension of the box. And you will have different energy levels. So it is acting like some sort of atom, the center over here. So when it is acting like an atom, this will have different energy levels: ground level, higher level, and other levels. And if now this electron uh, can be excited, can be thermally excited, or can also be excited with help of some other radiations. And when it de-excites, so it emits a photon which has an energy equal to the energy difference between two levels, which you well know. This phenomena is well known. You can call it to be fluorescence, that if you excite some of the electron in the ground state to some higher energy level, it will emit the energy which is a characteristics of its energy level. And that is what how it is calculated. Here for 2 electron volt, lambda is calculated to be 620 nanometer, which is red. So here you have different crystals: lithium chloride, sodium chloride, potassium chloride, cesium chloride, potassium bromide, lithium fluoride, like this. So this is their uh, energies of this uh, emitted radiation in the electron volt. And for KBR, this is coming out to be red. This is also called F center. So now this color will appear because just like you can see that wavelength emitted here is red. So the crystal will appear at this point of red color. So that is why it is called color center. It is also known as Farb center or F center. Actually, this Farb is a German word. So possibly there was some German scientist who invented that. So instead of saying it color center, he called it Farb center. Or this is also called F center, for F for Farb, like this. So uh, now, if this excitations level lie in the visible spectrum, they will show colors. Though they are defects in the system, so because of these defects, some bound electron pair will cause this color due to excitations. And here you can see that from lithium chloride to cesium chloride, how this spectrum is shifting. This is near um, 4000, and this is a blue color. It will produce, this will produce slightly green color because of this wavelength, and it is shifting towards the red. So from the blue to the red, you have the entire spectrum of the colors in different form of crystals. Now we see here, these are the crystals. These are different crystals, and you see that they are very colorful, and they are colorful because of the defects. And the defects are produced in them due to ion irradiation or thermal treatment, or there are some ways by which you can produce these point defects. And because of the characteristics of this crystal, you have a blue color. And because it may be maybe lithium chloride, so it's giving you a blue color depending on this energy excitation levels. And you can see that on the right hand side, this is some ornament and the different kind of crystals, which you see, the color crystals. These are produced uh, with the defects, actually, by creating defects in them. So you have some stones and which are used in the ornaments and decoration pieces, different stones of different materials. So generally they are because of the defects produced into the system. Now, this kind of system does not have any dye or something, or just like we have our clothes, a different color actually coming from the dye, and that's how our clothes are of different color. But here, generally in this type of crystals where you cannot color them, it is not possible because any color will come out by just single washing if you color them. So to have this permanent color, this feature of permanent color in the ornaments, to produce defects in them. Once you have a defect concentration, you will have they will always be having this beautiful colors. This is how one can have. Now, growth and synthesis, how one can actually produce the defects. And it is, I will get, it will be better if you get some text from somewhere and then read it from the text from there. Okay, so it's not much to tell us except that there is a technique how you do that. So how you produce that is heating to high temperature and quench it. So you produce it at very high temperature, and you know that thermodynamically you have learned that as you go to high temperature, you produce more and more point defects. Okay, and when you have produced large effects and then quench means you instantly cool it just by putting them into some cold water or something. So what happens is that when you quench them, instantly cool them, suddenly cool them, this point defects remain frozen where they are. Now even though you have brought the material to the lower temperature, room temperature, but this defects will remain frozen as it is because they did not get time to equilibrate, and these defects are produced permanently. Unless you heat the system again up to that temperature, these defects will remain like this. Okay, heating in reactive atmosphere. So you can have some gases and allow to diffuse inside the crystal and let them react. This is also one way to produce defects. Heating in vacuum, oxide may lead to loss of oxygen. So if there are some oxide, if you want to remove oxide vacancies, you heat in vacuum, some oxides will be removed from there permanently. So that way you can create some vacancy. So you can also do it with some, okay, let me not talk about this plastic deformation, not necessary. Ion irradiation. So if you have energetic beam of electron or some ions and irradiate them on material, you can produce permanent defect inside the system. And ion beam implantation, neutron irradiation, these are the techniques, simply written somewhere. You can read them in books. So I'm not bringing that here, that you just have a beam of neutron and you irradiate them. These are just method, and you can read them simply from some book. Okay, so type of solid solutions, I think this I leave because it is not there in your now I will come to line defects. This is called dislocations. Okay, they are bringing some type of plastic deformation, which is a permanent deformation to the systems. And I will just give its definition to you, and rest is a material you can read it. So now comes a line defects. So point defects, you already have seen that it is basically observed at a given point, or either one atom is missing or a group of atom missing from some position. So that's come in the category of point defects. Now line defect, as the name suggests, it is going along a line. If you see, the defect is propagating along a line. So these are called one-dimensional defects. And, they are called dislocations. So dislocations are two types. There is called edge dislocation. Okay, unless you understand the geometry of it, you will not understand what is a screw dislocation, what is edge dislocation, and there is something called Burgers vector in it. And so I will come to this and just explain to you the technical point. Now look at this. This is what is called a typical edge dislocation. Look at this diagram here. Now you see the 1, 2, 3, 4, 5, 6, 7. You have 7 atoms, and then in the next plane you also have 7 atoms and 7 atoms, and here you 6. You see the one plane here is missing. This atomic row which was there is missing here, and now this atom is bonded with this one, and this atom is bonded with this one. Now you can see that. So this kind of dislocation is called edge dislocation, because you see there is an extra plane. It seems that in the entire crystal you inserted the extra plane up to some half distance, and after that you left it. If this extra plane was inserted completely, there will not be a defect. So you brought some extra plane of atoms and you inserted in between and left just here. So at this edge, this would create an edge dislocation. So how to differentiate the edge dislocation? And Berger vectors is also there. I will talk about it. So you just see any, make any circuit around this dislocation point. So this is the point where this dislocation is there, and now you make any, start from, let us say, this point. Okay, now you move from this point, one, uh, 1, 2, 3. So you have moved 3 vertically down, and let's now from this point move 1, 2, 3. Okay, so you have 3 moved down and 3 you have uh, moved horizontally. Now move 3 up from here, 1, 2, 3. Now to complete the circuit, you should move right by 3. So 1, 2, 3. But you see, we started from here. 3 we completed here, but we started from this point. So something remained. यहाँ पे जो कुछ जगह है वो खाली रह गई है. इसको कंप्लीट करने के लिए जिस वेक्टर की जरूरत होती है उसको हम कहते हैं बर्जर्स वेक्टर. तो सर्किट को क्लोज करने के लिए अगर आप 3 स्टेप यूं चले, 3 स्टेप यूं चले, 3 स्टेप यूं चले, 3 स्टेप यूं चले, तो ये जो सर्किट कंप्लीट नहीं हुआ, बिकॉज ऑफ दिस, इज बिकॉज ऑफ दिस डिसलोकेशन. अगर हम ये कहीं और जगह करें, डिसलोकेशन को हटा दें, तो ये हमेशा कंप्लीट होगा. देखिए, 1 2 1 2 1 2 1 2. हम जिस एटम से चले थे उसी एटम पे वापस आ जाते हैं, लेकिन अगर डिसलोकेशन है उस जगह में तो हम वापस उस पॉइंट पर नहीं आ पाते. एंड टू कंप्लीट द सर्किट, whatever vector is needed, that is called Burgers vector here. So now you can see that when Burgers vector is perpendicular to the dislocation line, this is called edge dislocation. Now what's a dislocation line? This dislocation line is perpendicular to the plane of this screen going down, because you see this edge of the atom, you go along the edge of this atomic plane, so you will go perpendicular down, and the Burgers vector is there in this plane. So when you have edge dislocation, this is the distinction of edge dislocation, that this Burgers vector will always be perpendicular to dislocation. So when you have Burgers vector perpendicular to dislocation line, it means it's edge dislocation. This is the clear distinction about what you can define as a edge dislocation. Now, I tell you the second type of dislocation. This is called screw dislocation. So screw dislocation is actually, as the name suggests, it is as if, with respect to certain point, as if you have rotated, your crystalline plane. Actually, if you see this figure, if let us say this corner was put this corner, there will not be any dislocation. It would be a perfect crystal, and this would come here, this would come here. Just from here, this is, you cut it from here and you give it a push. and now this atom is connected here instead of there. So now this region, this kind of dislocation which is produced by rotation is called a screw dislocation. It is as if you have, you know, rotated the upper part, keeping the lower part as intact. Now again, you can make the Berger circuit here and you find out. Now the dislocation will propagate along this line, along this curve. So if you go here, you see, if you go in this direction here, you will see that this um, dislocation will propagate along this line. So this dislocation line is along this axis where my cursor is moving, along this axis, because inside the crystal this dislocation will be moving up to certain length, up to certain length, some micron length, where it will be propagating. So this is the direction of dislocation line. Now let's make the Berger circuit and see. So idea is to include the dislocation point and then move. Let us say start from here. You 1, 2, 3, 4. Okay. Now 1, 2, 3, 4, 5, 6. And now because I came 4 down, if I just want to move uh, 1, 1, 2, and then 1, 2, and 1, 2, 3, 4, 5, 6. I started from here. So still if I come 2 there and 2 there, though I went 4 step, but I could not complete the circuit because this is still left behind. So to complete the circuit, I need to draw a Berger vector here. The 2 step up, 2 step down, because I went 4 step vertical. So these are also 4 step vertical, but it did not complete the circuit. So I need to draw an extra vector here, which is called Berger's vector. Now you can see this Berger's vector is parallel to the dislocation line. It is different from the last case where you saw that Berger's vector is perpendicular to the dislocation line. Here, the Berger's vector, you can see in 3 dimension, you can visualize it. This Berger vector will be parallel to this dislocation line. So when Berger vector is parallel to this dislocation line, this is called screw dislocation. So you can have screw dislocation, you can have edge dislocation, or you can have both. Okay, at the same time, both kind of dislocations are also possible, and they are expressed in this diagram here. You can see that this is a screw dislocation coming, and at this point B, you see that some edge is coming up to here and it just terminates in between. It's not coming up to this point. So you have here edge dislocation, here you have screw dislocation. So can be a mixed kind of thing can also be there. And only with the help of Berger vector, you can find out whether it's a screw dislocation or edge dislocation. So what is the um, benefit of this dislocations is that your crystal lattice is basically distorted and you lose some degree of order at some point, and it increases the elastic or mechanical properties of your system. Your system, if you have large number of dislocations in the system, it can be very brittle. I mean, just with the very little impact, it can be broken into pieces. So if you see that some of the material you have seen, they are very fragile. Just when you hit them, they are shattered into pieces. So when you have some defects and dislocations trapped in the system, that is how it becomes. If it is a perfectly crystalline system, it is difficult to break it also. It will also be elastic, will not be broken so easily. So they changes the mechanical properties of the system. The presence of this dislocations, screw edge, they have, and this line defects generally have produce a plastic deformation, is some kind of permanent deformation introduced into the system. Though it is very easy to heal the point defects by thermal annealing. You just anneal it thermally and then cool down slowly. So thermal equilibrium is achieved, and many of the defects, point defects from the system will be removed. But it's very difficult to remove this dislocation from the system. So they have an advantage and disadvantages both. So it depends on what applications you're looking at. So I'm not talking about the surface defects because this does not cover your course. So I think that's it that I had to talk about. And now I'm ready to have some questions, take some questions from you if you want to ask me some questions. I'm just waiting for 4 or 5 minutes. So I have some chat, it seems. And okay, now you can listen to me. This is a chapter of defects. In this, I have covered to you the main aspects of point defects and line defects, and discussed with you the conceptual things. And it is already given in Charles Kittel. The book also I have shared with you. So depending on the what kind of questions you may face, you can just read it, and the rest of it is just a reading. I just need to talk about to you. Just I have to give you some conceptual understanding of what uh, line defects are, what point defects are. I've also given you an assignment to calculate the equilibrium number of defects at any temperature T. So hint is also given. There is a numerical also you can solve yourself. But this assignment you have to submit it to me. Um, Let us say in 2 3 days, up to maybe Saturday or Friday. It will not take much time if you sit with it, and you can scan it using cam scanner at your phone. With your phone is an app, and you can produce just can have one PDF file. Everything can be in just one PDF file. If it is 1 page or 2 page, I think it will be maximum 2 page derivation. And then you can email it to me. It is available to you, or you can just put it on your MSc WhatsApp group, whatever you like. So that's it for today. I think if anybody has to ask anything. Okay, then I'm closing this meeting, and bye and all the best to you.